Our topic for today is section 9.2, which is Series and Convergence. And actually here is where we introduce the main topic of the chapter. So instead of giving you a formal definition of what series is and what do we call convergence of that series, let's try just to analyze one problem that's intuitively very close, I would say, to us. And then from there we'll kind of build the proper ways to discuss the issue. So here it is. Let's answer what is the sum 1 over 2 to the n when n goes 1 to infinity. So there are quite many things that might be confusing here. First of them is sigma notation. So what is the meaning of this sigma notation? That means sigma n equals 1 to infinity, 1 over 2 to the n. Sigma means summation. And then what do? You keep plugging the values from the lower number up until you reach the upper number, but if it's infinity, that means just never stop, intuitively. As I said, this is obviously a fairly foggy approach, but generally I would say the following. N equals 1 is the first value. When I plug it in, I'll get 1/2. Then sum says, and then add. When n equals 2, I'll get 1/4. When n is 3, I'll get 1/8, and I keep adding forever. As I said, notion is a little bit iffy, but let's see if we can make sense out of it. Basically, we can just illustrate graphically what this represents. We'll take a square, and then take a half of it here. So that's our first member. That's actually what we call A1. And then here's our second member, A2, which is 1/4. Here's our third member, A3, which is 1/8. Here's our next one that I didn't even write. Here's A4, which is 1 over 16. So this is A1 equals 1/2. A2 is 1/4. This is 1/8. This is 1/16. The next one will be 1 over 32, half of whatever's left. And 164, and so on and so on. And what will happen? We'll add less and less because these are really tiny additions, but generally at the end they will exhaust whatever's left uncovered here. And that leftover, actually we covered this first, then we conquer this, we conquer this, we conquer this, then this, then this, take half of what's left, take half, take half, and this part that's left diminishes quite clearly. So at the end what will happen, all these areas when we add them up, and that's the crucial word, cumulative effort, adding them up, this looks like it should be 1, generally will exhaust the whole area. So I hope that this makes sense, and basically that's what we do when we have a series. So here's definition. Let an, when n belongs to n, be a sequence, and let Sn. So generally when we talk series, we don't really discuss individual behavior of each of them. What we do is just add up the first n members, A1 plus A2 plus an. And then of course that list becomes longer and longer. So, or we also write this as the sum AI or AK when I goes from 1 to n. Those are called partial sums. So we build them, and then what do? We'll look for their trend. So if limit Sn for n, if it equals S exists, then we say that sum I goes 1 to infinity, AI equals S. we write, so we don't say, we write, and say that the series sum ai, I goes 1 to infinity, converges. So that's a definition. So I can say, oh, but that's not dramatically different from what we did in the previous section. We are just looking at the limit of a sequence, but that sequence is just not the one that's given. We just keep adding the numbers, so we analyze them cumulatively. We look at a different sequence of SNs, and then look at the trend of that one. But what's the problem? Problem is that very often ANs have explicit nice description. SNs are not always so easy to describe. So very often we will need to find this trend even when we are not able to really calculate SNs. We need some alternatives way to analyze the process. So that's one of the main ideas of this chapter. But today we'll mostly deal with this type of series, which we call geometric series, and then toward the end we'll just analyze one fairly irrelevant type of series and the ideas. That idea is unfortunately too much emphasized in your book, and I see students spend lots of energy on that method. That's really like side method that rarely is used, just in a very specific situation. It's called telescoping. So telescoping is among our strategies, the last one. You rarely do telescoping, don't overdo it. But let's focus on the geometric series. So this was the example of a geometric series, or geometric series. So maybe the subtitle is sequence and series. We need to explain them both. So when do we have geometric sequence? So geometric sequence looks like this. We have B1, B2, B3, B4, and so on. So that sequence is called geometric if the ratios are fixed. So if B2 over B1 is the same as B3 over B2, B4 over B3, and so on. Basically what? If we have BI plus 1 over BI is fixed, and then we call that R is the ratio of geometric series. So important property, and that, so example, if you look at the sequence, so here we're talking sequence, be careful about these words. Are we analyzing them individually, or we are adding them up and analyzing the sums? So here is 3, 6, 12, 24, 48, and so on. So generally this looks like a beginning of a geometric sequence. So why? Because 6 over 3 is the same as 12 over 6 is 24 over 12 is 48 over 24. It's equal to 2. So it looks like this is geometric sequence with a ratio 2. And there is important and trivial, like a little theorem, that actually if Bn, when it belongs to n, is a geometric, I'm going to the edge. Geometric sequence with ratio R, then Bn equals B1 times R to the n minus 1. That's very easy to establish. Why? Because, for example, between first and fifth member, so B1, B2, B3, B4, B5. Between B1 and B5, we made 4 times doubling. 1, 2, 3, 4. That's why it's n minus 1. So each doubling, each R-ing is times extra R, so it's obvious that this is the formula. All right. And then now we want to discuss also the sum of geometric series. So when we look at the geometric sequence and we want geometric series to add them up, we want to see how to calculate. So in this case, we can calculate Sn and then very easily conclude about convergence and divergence. So now we are talking about geometric series. I can keep this. So geometric series. In order to obtain the result that we need, I'd like to mention one fact, and that one is very useful throughout the chapter, and that will be that sum r to the I, when I goes from 0 to n minus 1, equals 1 minus Rn over 1 minus R, as long as R is different from 1. This is a famous formula. We should all memorize it and know it. Generally, it helps us then to get the summation formula. What is this basically telling us more precisely? It tells us the following. So let me prove the fact. Proof is fairly simple. While, what's this? 1 plus R squared plus R to the n minus 1. And I want to show that that's what it is. I will call this S. Is that healthy? Maybe I should. Okay, let me call it A better. Because if S, that looks like a limit of a sum, I better call it just A. And here is the great move. Let me multiply everything by R. And we get the following: R plus R squared plus R cubed plus Rn equals AR. And now we will subtract these. So what will happen when we subtract them? When we subtract them, there is lots of repetition. R on the second spot is the same as R on the first spot below. R squared the same thing, R cubed the same thing, although cube is hidden among the dots. Rn minus 1 to the left is also canceling the expression ahead of it on the left. So generally when we subtract it, just first member on upper line and the last member on the lower line are left. So we just get 1 minus R to the n equals A minus AR. And then we factor out A and divide, and we are done. This is A times 1 minus R. Then when we divide, we get our formula. So here is that summation formula. Once again, remember, this index here is by 1 bigger than this one. So if you stop at n minus 1, you will get n. If you stop at 10, of course, you will get here n plus 1. And then what? Then we have the following theorem. No, it's a big theorem. And it's theorem 9.6. It says a geometric series. Look, series, not sequence, so we are adding them up. Crucial thing is to read that word correctly. A geometric series with ratio absolute value of R greater than or equal to 1 diverges. If absolute value of R is less than 1 and greater than or equal to 0, then it converges and sum when n goes from 0 to infinity, a r to the n equals a over 1 minus r. Here is the crucial result for the homework today, and very often we'll use this fact. Please remember it carefully. This is generally sum of every geometric series with r less than 1, absolute value of r less than 1, because that's how all the geometric series look like. You have first member and then powers of r. So how do we prove this theorem? We'll actually, when we discussed convergence, we said find Sn and take a limit. We are lucky enough that actually a minute ago we developed a formula for Sn. So what would Sn be? Did I use n here in the formula? I did. So here it is. Sn is the first members all the way to the index n. So, so first n members are, so since I want n to label the length of the sequence, my running index must be different. So I cannot use n here, I'll use I. So I goes between 0 and n minus 1. Why is that Sn? Because if you remember, if you go from 0, 1, 2, 3, 4, you have 5 members. 0 to 9, it's 10. So generally, if you go all the way from 0 to n minus 1, you have n members. Because from 1 to n minus 1 is n minus 1, and then 0 index. That would give you Sn. So what would that be? Sum of a r to the I. And what would that be? Luckily, as I said a minute ago, we developed a formula for this. I can factor out tau a because of distributive law. Sum r to the I goes 0 to n minus 1. A minute ago, we had a formula for this, and that was a times 1 minus r to the n over 1 minus r. And all this calculation is done under the assumption that r is different from 1. Maybe I should have said that before. So if r is different from 1, I can do this reasoning. What about r equals 1? Then we need to analyze later on what happens. So we need to do that one individually. So that's it. We have Sn for all cases when r is different from 1. And then, according to definition, we need a limit. So what happens when the size of collection, because that's what n is, how many members will it take? When the size of collection approaches infinity. So we get a limit of a times 1 minus r to the n over 1 minus r when n goes to infinity. And then we need to know, to recall our limits from section 1 or from calculus 1. So here is what could happen. If absolute value of r is greater than 1, then what happens? This is a constant number. This is a constant number. If you raise number greater than 1 to infinity, you'll get infinity. Why? Because if you take like 3 halves times 3 halves times 3 halves, that's exponential function. With a base greater than 1, so that one approaches infinity, so this limit is infinity. It's infinity, positive. If r is positive, it's positive. So limit is infinity if absolute value of r is less than, greater than 1. What if absolute value of r is less than 1? Then, according to the properties of exponential function, if the base of your exponential function is less than 1, then this limit approaches 0. So in this case, this would approach 0. So our limit would be limit Sn would be 1 over 1 minus r, which is exactly what we said, but I lost that a times. So this is 1 over 1 minus r times a. It's a over 1 minus r, as we said. So once again, if absolute value of r is greater than 1, we get infinity. If absolute value of r is less than 1, then we get exactly what we promised. What happens if absolute value of r is 1? That's left. So what do we do here? Absolute value of r equals 1. Then interesting things happen. So we'll show you in a moment that the series diverges. That means it does not converge, but it will be different reasoning why it diverges. So let me now erase the board here and see what happened in these cases. So I'll do those cases separately. What if r equals 1? That means that our series look like this, like sum of a times 1 to the n when n goes 0 to infinity. What is that? It's a plus a plus a and so on. And that sum is just what? In that case, Sn is n times a, because you have an times, so limit Sn is infinity. Because you had like 7 and 7 and 7, so you get thousands of 7s, and that goes to infinity. But at r equals -1, something strange happened, and we'll analyze that in lectures to come. Actually, here's what happens. If r equals -1, then the sequence looks like this. Sum of a times -1 to the n, when n goes 0 to infinity, so you get the following. When n is 0, -1 to the 0 is just 1, so you get a. And then we subtract a. Then we add a. We subtract a, plus a, minus a, and so on. So what can we say? We do not get like infinite, but this is a different reason why this is not converging. Because S1 is just a. S2 is a minus a, which is 0. S3 is again a, S4 is 0, and so on. So what happens? Does the limit Sn exist? It does not. It does not exist. Why? Because we have that alternating limit. I don't know if you remember from calculus 1. Generally, this sequence goes like this. It is a, negative a, negative a, negative a, so it never stabilizes. So that's why limit does not exist. It's called oscillating. Oscillating sequence. And since it's oscillating with big amplitude, fairly big amplitude, then the limit does not exist. So to summarize, we showed that at 1 and -1, it also diverges for kind of a little different reasons, but altogether we have the summary. So summary says, if r is by absolute value less than 1, here is the sum, it converges, and if it's greater or equal 1, it diverges. By the way, this is the case, this introductory example, we are really dealing with the geometric series where the first member is 1/2, and then the ratio is 1/2. So we would have here 1/2 or 1 minus 1/2, and we would really get 1. So probably this is the most important fact that you need to memorize today for practical purposes. So let's see something in this flavor. So let's practice problems. Shall I leave this? I get a good idea. So I'll leave it on the board so that we can call it when needed. So what's... Right, let's practice a few problems dealing with the technology that we just developed. So here's a simple problem, number 40. This one. Number 40. So we want to discuss the sum, and we go 0 to infinity. 6 times -4/5 to the n. And let me just copy somewhere here so that we have it as a reference. Sum AR to the n, when n goes 0 to infinity, equals A over n minus r, if absolute value of r is less than 1. Minus r, this is common. So, in this case, we recognize that we are dealing exactly with a situation like this one, starting with 0, ending at infinity. It's all exactly like in the formula. So, our A is 6, 1 is 1, our r is negative 4/5. That's it. So this will be 6 over 9/5, which is 30 over 9, which is 10 times. So this is just easy, straightforward application of the formula. Next problem deals with the same thing in a little different setting. And that is, how much is 0.9 periodic? This is actually what? 0.9999 and so on. So what would that be? So this is infinitely periodic numbers. And you will see in a moment that actually this is the case where this number is the same as 1.000 and so on. So generally number 1 has two different infinite periodic representation, one ending with all 9s and one ending with all 0s. This is different from what we know about finite presentation, where first digit being different tells you that numbers are different. Here, digits, this one has digit 0, this one 1, they are still equal because infinite presentations are a little different. So how do we establish this? Just using geometric series. It's actually 0.9 plus 0.09 plus 0.009 and so on. So this is basically infinite series, so sum of infinitely many individual members. And basically what? This is obviously geometric series, where this is your first member A, and then each member is 10 times smaller, so R equals 0.09 over 0.9 or any other, and R is 0.1. So this sum converges because R is less than 1, between -1 and 1. So we put A on top, which is 0.9 over 1 minus R, which is 1 minus 0.1, which is 0.9 over 0.9, and it's really equal to 1, as we expect. Similar problem, just with a little variation to keep in mind that length of the period also is important. Number 55, what is 0075 periodic? Be careful here, the period has length 2, so it will look a little different, but if you open it, it's not a big deal. Next one will have zeros, where we had before 75s, and then 75, and so on. So then, the same reasoning, this is your A. But the difference is, since these number 7 and 5 were replaced by 0, 0, and then 7, 5, that your R is now 0.01, because our number 7, 5 was pushed by 2 digits to the right. And that's it. So now S equals A, which is 0075, over 1 minus 001, and that's it. A little polishing. This is what? 0075 over 099. If we multiply it by 1000, you will get 75 over 990. And if we divide by 15, you will get 5 over 66. And then what? Obviously, if you are doing this as a homework or on the exam, good idea is to put this in calculator, 5 over 66, and see really if calculator will give you this presentation. I want to do one more problem that has this flavor, but this one is applied. So it's a word problem. It says the following: a ball is dropped from the height of of 16 feet. Each time it drops, each time it drops h feet, it rebounds 0.81 h feet. Find the total distance traveled. So we are assuming that it goes up and down forever and it never stops. So here's the story. In the beginning, that's our ball covers these 16 feet. So here it is, goes down by 16 feet, and that's the first distance it covers. Now it rebounds, and that rebound is 16 times 0.81, according to this information. If it drops h feet, this is the drop, rebound 16 times 0.81. But when it reaches that, this is something that they didn't tell us, but we have to conclude that ourselves. Then, that's my red, it just falls down the same distance. So now it goes down, I draw that red, the same 16 times 0.81. And what happens after that? Then 0.81 of that red goes up to the green. So in that green you would have what you have 0 times 16 0.81 from previous time, 0.81 times another 0.81. So it's always 81% of what it was before, like radioactive decay. And then what happens? We go down the same distance. By the way, 0.81 times 0.81 is just 0.81 squared. See that exponential function. So both green and red are 16 0.81 squared, and now by analogy, we don't have to analyze it too much. This is 16 times 0.81 cubed, the same thing down, and so on. So this is the second pair, and then first pair. And this looks like geometric series because if you look at this couple and this couple, this sum is 0.81 of the previous one. Unfortunately, our symmetry is a little bit ruined on the first one. And then what do? We can analyze geometric series with all the members except the first one and then add 16 at the end. And that's how I did it in the lecture notes. But actually, I want to do it a little differently here. I will reestablish the symmetry. So I will assume, which is not correct, that there is also a red part here, also I read 16. Of course, that's not correct. So to balance it, I will just subtract 16 at the end. So this 16 balances this 16, and I'm okay, and I have a full symmetry. So what happens then, that it's very easy to control this. So S equals, my first stage is 16 and 16, which is 32. Then second couple gives me 32 times 0.81. So 16 and 16 is 32, both of them times 0.81. This one would be 32 times 0.81 squared, and so on. And then what? Of course, don't forget minus 16. That's it. Now I have a very nice geometric series. So what is this? This is the sum, 32 times 0.81 to the n, and then it goes 0 to infinity, and minus 16. Now I call the formula, this is my A, this is my R, so I get 32 over 1 minus 0.81, and minus 16. And then when you plug this into calculator and finish the calculation, you'll get 152.42. The answer is in feet. So everything is feet. So yes, this is the total distance traveled. So it was fairly straightforward. Now, I announced in the beginning there is one technique that just more curiosity, kind of, some, I don't know, exotic idea that really works very attractively, but they rarely use it. So don't try this idea too often. It's in your book, and your book gave you lots of time, I don't know why. But maybe it's neat, but it's nothing big, it's just one isolated technique that's rarely useful because you rarely get situations that look like this. And things really have to be very specific in order to use that technique, and here's the idea. So, I want to analyze some case example, it's called telescoping. So, analyze the convergence of the series I equals 1 to infinity 1 over I plus 1. And what happens? Just we are extremely lucky. Look how nice they are. They are clean numbers. There is basically what is this? 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 and so on. So numbers are nice and they increase at a very nice gradual level, and that gives us a chance to play one trick, as I said, nothing big. So here's the story. So what is Sn? 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over n times n plus 1. And basically what we are doing here, we are kind of doing like partial fraction decomposition. So since these two differ by 1, I'll write my 1 as 2 minus 1. And the same thing here as 3 minus 2 and plus 1 minus n. Basically, if they differ not by 1 but by 5, then I would need 5 on top, 1/5 of this. So this idea can be varied a little bit, and then what happened? First couple is 2 over 1 times 2 minus 1 over 1 times 2 plus, here is 3 over 2 times 3 minus 2 over 2 times 3, and plus n plus 1 over n times n plus 1 minus n over n times n plus 1. And what happens here? Generally, the way things were working in this problem, very interesting, is that basically we have some cancellations here. 2 and 2, 1, so you get what? 1 over 1 minus 1 over 2. The same thing here, we get 1 over 2 minus 1 over 3, and so on. On this one, we'll get 1 over n minus 1 over n plus 1. This is really like partial fraction decomposition. And here comes actually what makes this spectacular. As I said, but we rarely have this special situation. We just reorganize parentheses. So we get 1 over 1, and then minus 1 over 2 plus 1 over 2. Plus negative 1/3 plus 1/3. There is 1/3 here, 1/3 minus 1/4 that's hidden among the dots. Negative 1 over n plus 1 over n and minus 1 over n plus 1. So generally each second member coincides with the first member of the next term. And when we reorganize that, what will happen? Everything cancels out, except the first and the last term. So basically we were able to calculate Sn, which almost never happens. Don't hope for this. I can even tell you that on the exam this will not show up. So just, because sometimes I see students trying this idea like on 3 out of 10 problems, and definitely I will put this idea on 1 problem or none. So don't overextend this idea. So why is this so good? Because then it's easy to see if this converges, because then I have a limit Sn when n goes to infinity is a limit of 1 minus 1 over n plus 1 when n goes to infinity. 1 over a huge number approaches 0, 1 minus 0 is 1. So we concluded that this sum exists, and even know that it's equal to 1. As I said, this is very special, neat situation. Interesting trick, nothing big. This is not conceptual thinking, this is just a lucky situation. equation. But now comes something, even if it's the end of the section, this is probably one of the most useful facts that we'll learn in this chapter. So please pay attention to our next theorem, and that's called Divergence Theorem or Nth-term theorem. So, Divergence Theorem. Or it's called in your book, I think, Nth-term theorem. Or N-term test. Maybe test. Great test. So what is that? Basically it says the following, here's the theorem. If some an when n goes 1 to infinity converges, then limit an when n goes to infinity equals to 0. The theorem is fairly easy to prove. Why? Because, and that's not a point. So let's say, so what is Sn? Is A1 plus A2 plus A. What's Sn minus 1? That's A1 plus A2 plus An minus 1. So basically, if you compare those two lists, they are almost the same. All this part is the same, just Sn has an extra member. So we can say here that Sn is Sn minus 1 plus An. So if the limit of if limit of Sn exists, and it's equal to some number S, then what do? We look at this Sn equals Sn minus 1 plus An. Then we can say the following, that Sn minus Sn minus 1 equals An. So limit of An when n goes to infinity is limit when n goes to infinity Sn minus limit Sn minus 1. How much is this limit? We said this. How much is this one? The same as, just goes one step later, but generally it has the same trend. So this is the proof. Why it has to be that way? Generally what this proof does is the following. You know, I very often think of a metaphor for convergence of a series like there is a bucket. And then individual members are dropping. So here is A1, here is A2, here is A3, here is A4, and they are dropping in here. So the question of convergence divergence is, will the level in the bucket stabilize or it will overflow? Overflow is divergence for positive numbers. So generally what this says, if you hope to not to overflow, to stabilize, you better make it sure that your drops are simple, that your drops are small. So basically what it says is, if it's better way to think of it is, if your drops are not small, forget about stabilizing, you will for sure overflow. And basically that's the way how we will apply this theorem. So let's make it sure that we understand the ways to apply it. Generally what you apply is the following. That's how that nth term test looks like. So you calculate the limit of individual members, not of S. And then what? You either get not zero, or you get 0. If you get that limit is not 0, then you immediately say the series cumulatively diverges. That means drops are not small, things cannot stabilize. But here's where students very often use this test wrongly. What if you get a limit to be 0? You cannot make conclusions. Keep testing. That's just your first kind of requirement. You passed your first test. You cannot conclude that because of that. So drops are small. Actually, the question is, are they small enough? and that's where additional testing is needed. So this is not the test that will qualify series for convergence, only used to disqualify it if it fails. So it's really failure instead of success test. So for example, let me go with one illustration. Here it is, number 61. Analyze the following series sum, and it goes 1 to infinity, 3n minus 1 over 2n plus 1. So for this series, it's quite obvious that numbers are too big, this will diverge. So formally, what do we say? This is your an, individual, not SN, just individual. Limit of an when n goes to infinity equals a limit when n goes to infinity 3n minus 1 over 2n plus 1. If you divide by n, you will get the limit when n goes to infinity 3 minus 1 over n plus 1 over n. You know, all the business, this approach is 0, so this limit is 3/2. So it's upper line, this limit is not 0, series diverges, problem solved. So nothing else. When we find that series diverges, we don't analyze it further.